This is the last lecture for the addition reactions of organic chemistry. So as a quick review, last lecture we looked at the addition of bromine as Br2 to alkenes. We also looked at the addition of bromine molecule in the presence of water or alcohol. As we saw, that was a regio-specific reaction, also stereospecific because of the trans product that's produced. Next, we looked at the addition of polar molecules to alkenes, and specifically we looked at HBr and HCl. You should remember here that it's actually HBr, polar molecule, because this is a polar covalent bond, because this bromine is more electronegative than your hydrogen here. Hence the electron density is closer to the bromine in HBr or the chlorine in HCl. Next, we looked at the rearrangement of carbocations. Don't forget, once you form your carbocation as an intermediate, it's possible for rearrangement to occur, typically going to the most stable carbocation. Next, we looked at the anti-Markovnikov addition of HBr. Just to refresh your memory, the Markovnikov addition involves the hydrogen of the reactant going to the alkene, the carbon of the alkene that has the most hydrogens. But this was an anti-Markovnikov, and don't forget that's using the peroxide. And lastly, we looked at the addition of water, hydration, to alkenes. There was a problem, however, that we encountered with this reaction, and that is, even though the major organic product is the Markovnikov addition, there is the possibility of rearrangement due to the formation of the carbocation intermediate. So in this lecture, we will look at the addition of water, hydration, to alkenes, but to give here the Markovnikov addition without rearrangement, special reagents that are used here, and also the hydration or the addition of water to alkene in an anti-Markovnikov sense, to give the using hydroboration to give the anti-Markovnikov addition. Next, we will look at the addition of carbenes. We covered that when we looked at carbenes as a reactive intermediate, so that will just be a review. Next, we'll look at the reaction of oxygen to alkenes. That's known as an epoxidation. It's really an oxidation. Another term is an oxidation, but it's the addition of oxygen to an alkene, which by definition is an oxidation. And then lastly, we look at the addition to carbon oxygen double bond. I just recall here we'll also look at the addition to carbon-carbon triple bonds. So let's begin. The Markovnikov addition of water to alkenes. As you can imagine, if you want to add water to alkenes without rearrangement, just using water and acid as a catalyst will not be sufficient, because many products are possible. So this can be accomplished by mercuration and demercuration reaction. So let's look at the details here. So here's an alkene. Notice this has a carbon with 2 hydrogens and a carbon here with 2 alkyl group. Reacting this with mercury acetate. So remember, mercury is one of your transition metals, so it's pretty large, and the acetate here is a good leaving group. So the reaction of these 2 electrons with this electropositive mercury breaks off the acetate as a leaving group. You will recall again that it's a bridged intermediate as shown here. It's a bridged intermediate. This looks like it's an error. This H should not be there. So it's a bridged intermediate in which mercury sits between these 2 carbons because it is so large. So that's the intermediate. Let's see what happens next. The next step is in a solution of water, because water is nucleophilic, as we can see here. These electrons will attack this carbon. Why that carbon? Because this carbon is more carbocation-like because of the 2 alkyl groups that are bonded to this carbon compared to this carbon that has only hydrogens. So it is again a regiospecific reaction attacking this carbon to form this intermediate. Of course, we have 2 hydrogens here, so here they are, which is a positive carbon. So losing one of these hydrogens here gives this intermediate. So that represents the first step of the reaction. I should point out here also that it's possible in an alcohol. By the way, these 2 electrons are really on the oxygen, acts in the same way as water, attacking the carbon that has the most alkyl group bonded to it to form this, and of course this loses your H plus to form this in a first step of the reaction. In the final step, this is reduced to H using sodium borohydride. As you will recall, that is a reducing agent supplying H minus. So this is just basically a reduction of this over here. And as you will see, this is the alcohol. So it's the addition of H2O across the double bond of the alkene. So here is a overall example. We have here a unsymmetric alkene where we have 1 hydrogen here and none here. So in a Markovnikov sense, we'd expect hydrogen to add here and the OH to add here. Using this set of reagents, however, we will get a product in which there's no rearrangement, because notice there was not a open carbocation formed. It was a mercury mercury ion, cation that was formed. So you can see here this is the major product, and it's also the Markovnikov product. Let's look at how do we get the anti-Markovnikov addition. Let's say you wanted the reverse, the addition to be the reverse of the Markovnikov. So let's look at the anti-Markovnikov addition of water to alkenes. As you can imagine here, this has to be a different set of reagents. Cannot be mercury and salt and water, but something else. So let's look at this reagent. It's borane. You'll see it in some books as diborane because it's a dimer. It exists as a dimer. But the bottom line is that it's a cyclic reaction. Some folks describe it as a concerted pericyclic reactions, where these electrons come here and these electrons come here, forming this type intermediate. So once again, so these electrons will come here and these electrons will come here to form this type intermediate. But notice there are two possibilities. So we can add it like this, or we can turn this around and add it like this. As you can see, an analysis here of the initial product shows that this is more stable. We're defining stability here as steric interaction, or the reduction of steric interaction. This carbon has two hydrogens and the boron. Over here, this carbon with the boron has two alkyl groups and the boron. So therefore there is a lot more steric interaction right here compared to the interaction right here. So this is more stable due to reduced steric interaction compared to this one. So you would expect this to form in the majority compared to this other product. The next step, as you can imagine here, is to get this off. We can get that off by an oxidation reaction in which H2O2, hydrogen peroxide, in the presence of base converts this into the OH. So this becomes the major product. Why the major product? Because it came from the major product from the initial addition of borane to the alkene. Of course, this was the minor product from the previous reaction. So the oxidation of the boron here using hydrogen peroxide gives the minor product here. So this gives a summary here. So here we have the same molecule, 2-methyl-2-pentene, using diborane. Notice it's diborane now, but it can also be written as B2BH3. Followed by oxidation gives us the major product, the antimycognicov addition as the major product. Using mercury acetate in the presence of water, followed by reduction, notice a two-step reaction, gives the Markovnikov product as the major product here. So just to review, the major product, or the Markovnikov product, is the hydrogen adding to the carbon which has the most hydrogen, and here it is. And of course the OH adding to this carbon with the least number of hydrogen, which is 0. So here is that. That's the Markovnikov addition. Let us review the addition of carbenes. So this is a carbene. You may recall a carbene here. This is a singlet carbene. And notice the properties here. It is a nucleophilic because of the electrons in the sp2 orbital, and it's also electrophilic because of the empty p orbitals. Don't forget, electrophile or electron loving species, positive or partially positive, needs electrons. Nucleophiles are nucleus loving, loves positive, so it has electrons, or it's negative or partially negative. So as you can see here, the electrons can form a bond here, and these form a bond here because of the nucleophilicity of this region and the electrophilicity of this region. So what's formed here is a cyclopentane. You will recall also that this is a very common type reaction that's used in organic chemistry for forming cyclopropanes from alkenes, and that is the Simmons-Smith reaction. Simmons-Smith reaction, where we have here CH2I2 in the presence of zinc and copper. So what's generated here is not really the active carbene, but a carbenoid, which behaves much like a carbene, to add right across here to get this. Notice this is a bicyclic compound. So you may want to review on the naming of this, where these two carbons here are the bridge carbons, and these are the bridge head carbons. So it's a bicyclo-4,4,1,0 heptane. Just to review: 4, 1, 2, 3, 4, 1, and 0, because there's no carbons here in this bridge, and heptane because there's 7 carbons, and it's bi because it's 2 cyclic rings, and of course cyclo. So another example here is the same compound we had before, but in this case the reagents are different. This is for the Simmons-Smith reaction, so it's really the addition of a carbene to that alkene to form the cyclopropane as our product. Let's now look at the addition of oxygen to an alkene. As we pointed out earlier, that's really an oxidation, isn't it? Because by definition, oxidation is the supply of oxygen. And of course, as you know, the other is removal of electrons and or hydrogens. But a main definition is the supply of oxygen. So let's look at this alkene here, styrene. If this reacts with metachloroperoxybenzoic acid, it's a peroxy acid or peracid. Why is that so? Because it has an extra oxygen here compared to benzoic acid. So that means that it can supply an oxygen to this double bond to form an epoxide, also known as an oxyrane. That's an IUPAC name for the epoxide, is an oxyrane. In the process, the product is a metachlorobenzoic acid. This is a benzoic acid, as you can see from this region here, and this is the peroxy acid. There are others that are used, such as trifluoroacetic peroxyacetic acid, but this is the most common, MCPBA, metachloroperoxy benzoic acid. So let's see what the mechanism is. So here is the peroxy acid, or here could be the metachlorobenzyl phenyl region, but let's write it like this. So you can see here that these electrons can come here to form a bond. This goes on to oxygen, then this bond breaks to form over here, and this picks this up as the carboxylic acid. So again, this is described as a concerted reaction. Concerted, everything happens, the bond breakage, all the bond breakage and all the bond formation occurs in one step, a single step. There are no intermediates. So this is a reaction to give an epoxide from an alkene, given this mechanism here. Notice again, this is the oxygen that's here. So you should be aware of that. So again, as you study, you should be able to imagine what type of experimental evidence can be carried out with these type of reactions, such as isotopic labeling and also kinetic isotope effect on these type of reactions. Here's an overall reaction here. So we have cyclohexene, MCPBA, that's the way it's typically written, MCPBA for metachloroperoxybenzoic acid, to give this epoxide or the oxyrane. Let us turn our attention now to look at the addition of organometallic reagents. You will recall that a very common organometallic reagent is the Grignard reagent. Let's see what's the difference here between the previous reagents we've looked at. This is RMGX. So here is a bond from the carbon of the alkyl group to magnesium. looking at the periodic table, you'll see that carbon is to the right of magnesium, which means that carbon is more electronegative than magnesium. So therefore this bond here, right in the middle, is a polar covalent bond. In some cases it's actually described as an ionic bond, because these electrons are closer to the alkyl group, which is more electronegative for these type compounds, compared to the magnesium, which is more electropositive. With that said, this is partially negative, and the reaction with a carbon oxygen double bond, you can see here it adds here. So this is a regiospecific reaction in terms of adding organometallic reagents to carbonyls. By the way, this should be carbonyls. I'll make that correction before posting the slides. Reaction to carbonyls. So as you can see, this is really a regiospecific reaction compared to the reactions we have done before with the addition to alkenes, because alkenes were carbon-carbon double bonds in which the electrons were essentially equally distributed between those two. Here, these 4 electrons here, a sigma bond and a pi bond, they're not equally distributed because the electrons are more towards the electronegative oxygen in this case compared to the carbon. So as you can see, the reaction here takes place because the nucleophilic R attacks the electrophilic carbon, and of course we have the electrons going off here to form the anion, which is now a salt. As you can imagine, because it's organic chemistry, we prefer not to work with a salt, but the actual organic molecule. In this case, it's an alcohol. So in the presence of an acid, we have an acid-base reaction where H plus here adds to this oxygen to get the alcohol. So that's a quick summary of the slide. The R of organometallics are nucleophilic. Its reaction with carbonyls, don't forget its carbonyls, is regiospecific to this carbon because it's electrophilic to form this alkoxide salt. This alkoxide salt in the presence of an acid, because it's a base here, can give the alcohol as a product. Some examples here. So if you have formaldehyde, for example, 2 hydrogens, electrophilic carbon, nucleophilic carbon here from the grignard, followed by hydrolysis, gives you an alcohol. Notice it's a primary alcohol that's coming from formaldehyde. Here is an aldehyde because it has one alkyl group reacting with a grignard reagent here, followed by hydrolysis, gives this as a product. Notice it's a secondary alcohol. So an aldehyde reacting with a grignard or an organometallic, this could be organolithium, gives you a secondary alcohol. And as you can imagine, if you had a ketone such as this acetone reacting with this sequence of reaction, should give you a tertiary alcohol, as shown here from this as your reactant. So you should be comfortable with these type reactions. Let us look here at an application of that material we've covered here. So we're looking at the addition reaction shown below of the organometallic here. This organometallic is methyl lithium. Notice again it's the same type reagent as the organomagnesium, the Mokagnikov. So lithium is even more electropositive. Look at your periodic table and you'll see that it's even to the left of magnesium and further up. So it's more electropositive. So you'd expect this bond here, the carbon lithium bond, to be just about ionic. Its reaction with this carbonyl, however, followed by hydration or acid-base neutralization, gives this as the major product and this as the minor product. So as you can see here, these are diastereomers because this remains the same, but there is a change in stereochemistry here depending on how this reaction occurs at this end. So how can we predict the major organic product for these type reactions? The next slide shows that. Here is a model that's used here. So let's briefly look at this. The lithium, as you can imagine, is electropositive, so it will coordinate with the oxygen of the carbonyl. The nucleophilic CH3 is delivered here. But what's important here is that this comes in from the side of the largest group. So the largest group is opposite. Notice it's the largest group from the adjacent carbon. This is really your Newman projection that we did way back when we started the course. So this is a Newman projection. So this is exactly opposite to the group coming in. So this is, in your text, you'll see described as the large, and this is the medium group, and this is the small group. But the main thing here is that the geometry is opposite, the large group is opposite to the nucleophile that's coming in. When that happens, we have a product, and followed by hydrolysis, we get this as our major diastereomers. This rule, or this rule, I guess, is known as the steric control of asymmetric induction. Sterics, again, here makes reference to the size of the groups that are involved here, and in particular the size of the group on the adjacent carbon to the carbonyl that should be exactly opposite to the entrance of the nucleophile. Let us look at this one. Again, this should be carbonyl, because I didn't change that. I'll change that again on this slide before I post them. So this is the addition of hydride to carbonyls. Really reduction, because as you will recall, reduction is the supply of electrons, and you will recall that H, the hydride, is H dot, which has 2 electrons. H with 2 electrons, a pair of electrons, that's a hydride. H dot is a hydrogen atom or radical, and of course H plus is the proton, but here we're talking about the hydride, which is H 2 electrons and negative charge. Let's see if we can explain this. So here we have lithium aluminum hydride, which of course, as you will recall, supplies H minus, the hydride ion. This is the electrophilic end, so you'd expect it to bond here, and the electrons go up, just as we did for the organometallics. And of course, after hydrolysis, we get the alcohol. But notice for this reaction here, because this is a cyclopentanone, we have here the equatorial and the axial as the product. Notice that they put here a tert-butyl, a large group in the equatorial position. Why? Because it tends to maintain the integrity of this conformer. Remember, we did conformations when we started earlier in the course. So this large group here in the equatorial position maintains the integrity of this conformer throughout the reaction, as opposed to ring flipping. So the H minus can come here to form this product, which is the lower percentage, or it can come from here to form this product, which is the higher percentage. What's interesting, however, is that if we should use here lithium hydride tri-sec-butyl group here. In other words, we have a hydride here, but it's bonded to a very bulky sec-butyl and 3 of those to the boron. So it's a very bulky reducing agent. Very bulky reducing agent. Notice it's reversed. We have 4% of the equatorial OH and 96% of the axial OH. So now comes the question, how do we explain this observation? Before we look at a possible explanation, let's just see what's the basic difference. Let's just make the observations here. The reactants are the same reactant for both reactions. The only difference is the size of the reducing agent here. This is a very bulky reducing agent, and this is not. So let's look at the explanation. As you can see here is the cyclohexanone. This is the tert-butyl group here to maintain integrity of the conformer. Here we have equatorial attack because there is a lot more space in the equatorial position because we have hydrogens here and here. So there is more space in the equatorial. However, this is now less stable once this is formed because we're putting the large OH group in the axial position. You will recall that's less stable because we have here hydrogens here that are in the axial position. So we have here a hydrogen here, and we have another hydrogen here, and of course we have some hydrogens back over here. So because of the interaction between these hydrogens here, this is a less stable thermodynamic product because of steric interaction. So you'd expect here well, let's look at this one now. The attack from this side gives you the more stable product, which is the equatorial, but as you can tell here, it has to compete with these hydrogens here that are in the axial position. So coming in, it's blocked by these hydrogens here. So there's less space for the nucleophile to come in to this carbon from this side because of the axial hydrogens. However, it gives a more stable equatorial product. So to explain the previous reaction that we saw on the other side, the less bulky reducing agent H minus would prefer to come in from this side to give this as the product. The more bulky hydride cannot come in from this side, so it prefers to come in from this side to give this as the product. So let's go back and make sure that it's consistent. So what we have here is the hydride anion. It can come in from here or from here. However, this is the major product here, so it would prefer to give the major thermodynamic product because it is small and can come in from this side, so the hindrance of the axial hydrogens here are not as much a factor as if we had a bulkier hydride. So once again, the small hydride anion can come in from this side to give the more stable product here. The more bulky hydride would prefer not to come in from this side because it is blocked from these hydrogens here, axial hydrogens. So it prefers to come in from this side here to give this as the major product here, which of course, as we know, is the axial or the less stable product here. So again, depending on reaction conditions or reagents that are used, you can be selective to get different products. Okay, let's continue. So let's look here at the reactions or the addition reactions involving alkynes. These are the carbon-carbon triple bond. Just to refresh your memory, as you can recall, these are nucleophilic. There are two pi bonds in a triple bond. So one pi bond can react with an electrophile to form a carbocation, and the nucleophile can react to form this. So if this were HX, for example, we'll see in the next slide, this would be the H, and this would be the bromide, for example, to form this. This is still an alkene, so as you can imagine, it can undergo another reaction here to finally form this as your product, final product. So let's look at this one as an example. So here's HBr. This is the electrophilic end of HBr. These are nucleophilic pi bonds, so it can react here to give this. Notice again, this should really be a bromonium ion right here, but I've written it in the open form just to emphasize here that gives the more stable carbocation, even though it's a double bonded carbocation here, which is more stable than putting it over here. And then the bromide comes in here to form this alkene. As you can imagine, that can add further to give this. Again, your more stable carbocation, a more Markovnikov type addition. And the bromine will add here to give this as your final product. If 2 moles of HBr are added to our carbon-carbon triple bond or our alkynes. Let's look here at the addition of water, hydration of alkynes. So let's say we have an alkyne here. Don't forget, this is a carbon which is bonded to a hydrogen. Let's say we wanted to add OH to this, to one of these triple bonds. One. Remember, there are 2 pi bonds. So is it possible to add OH across this? Don't forget, this is again H and H. So is it possible to add here H2O across this triple bond to give here a double bond? This is known as an enol. En right here, all. So it's an enol. If we could form this, however, this quickly tautomerizes. You will remember this from way back. Enols are not stable because the carbon-oxygen double bond, a more stable, stronger bond, so it quickly tautomerizes from the enol to the keto form. So this is called a keto-enol tautomerization. The equilibrium favors the ketone, and the T represents the tautomerization. So the question is, can we go from here to here? Let's see if that's possible. So what we can do is, you may recall here that this is mercury. So mercury added to, which is electrophilic in this case, added here. We have this mercury type ion intermediate. We can now have water attacking here, and notice the water will attack this carbon. Why this carbon? Because this carbon is more cationic like compared to this carbon, which has just one hydrogen to give this. This will continue here to react to give this as a carbocation, open one. But the bottom line is, we need to get rid of the mercury. We need not reduce it in this case, because it will automatically come off, because it's a true catalyst in the sense to give Hg2 plus to give our enol. So you can work through this mechanism here, but it's one that you should be familiar with. So this is the enol, which tautomerizes here to give here the ketone. So let's see. So it's possible to go from here, let's go back here, this pentyne here, adding OH to this carbon in a Markovnikov sense to give this enol, which gives the pentanone or the ketone. That's the Markovnikov sense. Let us look here now at, well, this is an example. So you have here again, this is H. So we have added the OH to this carbon to form the enol, and the enol tautomerizes to give the ketone. Let's look here at the reverse. Is it possible to add the OH here instead? So don't forget, this still has an H here. So is it possible to add the OH here and the H over here for addition of water? This, of course, would be an anti-Markovnikov addition of water to our alkyne. And again, it's an enol, so you'd expect the enol to tautomerize to the keto form here. In this case, it's an aldehyde. Same type of tautomerization as we have discussed in the previous slides. But so this is the final product. So the question now is, can we go from this triple bond here to add water across this triple bond using one of those pi electrons to give an anti-Markovnikov addition? Let's see if that's possible. Yes, it is. So let's look at the same type reducing agent that we had before, borane. So this is BH here, but instead of having BH3, we put here the bulky secondary isoamyl group. Two of these. So these are very bulky. As you can see here, this bulkiness makes this addition going to only this one more efficient. In other words, the reverse. Switching around to form the other minor addition will not be favorable. So this addition here is essentially 100% to give this as the addition of this borane, bulky borane here, where this bulky group adds to this carbon because it's just hydrogen, and the hydrogen adds to this carbon, so there's less steric interaction at this end compared to if it were added at this end or the reverse. As you can imagine, the oxidation of this group here gives us the alcohol, and this would of course be the enol, which quickly tautomerizes to give the aldehyde. So that's in essence how we would transform a triple bond into an enol in an anti-Markovnikov sense. And here's a summary. So here again we have the same molecule. Here's an H bonded to this carbon. If we should use a secondary isoamyl borane, it will add in a sense to reduce steric hindrance, followed by the oxidation would give the anti-Markovnikov addition to the triple bond to give the enol, as we've seen before, and that quickly tautomerizes to give the aldehyde. So as a summary, what we have here is, again, two molecules, the same. The only difference here is the reagents that are used. Using mercury as a catalyst, adding water, and of course acid, we get here the Markovnikov addition for the enol, which tautomerized to give this as the product, the pentanone. So you can see we're transforming this pentyne into pentanone. If you should use a different set of reagents, a very bulky reducing diborane here, secondary isoamyl times 2, this will add here in a sense to reduce steric hindrance, where the OH will add to this carbon to give this enol here, and the reduction, well, followed by the oxidation of the borane gives this enol, and the enol tautomerizes to give the pentanal, that's the aldehyde. So starting with the same molecule, we can get the aldehyde using this. Starting with the same molecule, we can get the ketone using a different set of reagents. I think this is the last slide, and it is. So this is the last lecture for the addition to carbon double bonds, carbon oxygen double bonds, and carbon triple bonds. So read upon this, or make sure you follow, understand the content here, and be able to apply it to solve different experimental observations. I think the next lecture will be on elimination reactions. We just have 2 more topics to cover: elimination reactions, and then we do pericyclic reactions. Okay, so continue to study hard, and I'll post the next lecture shortly. Okay, bye.